Okay, hello everyone. Maria, can you hear me?
Yeah, I can hear you.
Can someone hear me?
Yes.
I can hear you.
Someone respond if you can hear me.
We can hear you.
Okay, hang on. Let me see if I can figure out what's wrong here. Okay, I think I've got a lot of messages now saying you can hear me, so that's great. So hello everyone. I hope you had a good break, at least as good as it could be with confinement. So I want to start out just discussing the second exam for the course. So this is going to be, of course, very different from exam one. And it's going to be held at the usual class time, so 9:40 to 11 on April 9th. And we're going to use the B courses quiz function. So you all should have access to B courses. And within there, there's a quiz function. And that will allow you to put in your answers. And we'll just use true, false, multiple choice, and short essay response questions. And so I think this is maybe the most straightforward way to do this without people having to print and then scan the exam. And I will try to make the exam so that it's not going to take more than an hour for you in case there are technical difficulties. The exam will be open book and open notes. So you're allowed to use whatever notes you have, the slides we used in class, the textbook, problem set keys, etc. Any material assistance is fine. But as usual for any of these exams, you shouldn't have assistance from anybody else. So no contact with others. And I want to remind everyone that you're all bound by the UC Berkeley Honor Code. And you can find this code online. But of course, the repercussions for not following this and cheating are significant. And I want anybody who has concerns about the exam in terms of maybe Wi-Fi connection or something such as that, please send me an email and we'll try to resolve the problem. So the other thing I want to say is that really this is an unusual circumstance, of course, and we're not going to be giving a lot of bad grades here. In fact, as you probably know, everybody's grades have been converted to pass-fail at this time, and you'll have the option to change that to a grade, a letter grade, if you wish. But if you want, all of your grades can be pass-fail, and that's perfectly fine. And so we're really going to, from here on out, focus just on learning the material as opposed to trying to differentiate people by how they do on exams. So we will have exams, but in the end, it's really just as an aid to help you learn the material. So let me ask if there are any questions on exam 2 or grading for the course. Okay, I don't see any hands up. Oops, let's see, there's a... So there's a question, will we still have a curve? We're going to not curve this as usual. It's going to be really very difficult to fail this course. If you pay attention in lectures, then you should do fine and easily pass. In terms of letter grades, this will be not so harshly graded on a curve. It will be really skewed towards giving good grades. And so I think we shouldn't worry too much about bad grades here. If you are worried about receiving a bad letter grade, then I suggest you stick with pass-fail. Okay, any other questions?
I just wanted to remind everyone that the problem set is due today at 6 p.m. There's a submission on B courses under assignments, and you can upload a PDF copy of your problem set. If the PDF part is challenging, there's a lot of apps that you can get for your phones that just like convert pictures to PDFs that you can get for free. And it's super easy to use, and you just email it to yourself. So yeah, let me know if anyone has problems with that.
So there's a question from Lindsay. Do you change grading on Cal Central or emails to professors? Maria, what did we do with grading so far for the exams?
It's just all been on B courses.
Yeah.
I don't know. I guess it automatically probably gets uploaded to Cal Central, but I guess in terms of selecting the pass-fail option versus the graded option, I don't actually know how
Oh,
people would
oh,
do
if you're,
that.
Lindsay, if you're asking about how to change your option, I actually, I don't know the answer to that. You
Okay.
should do it on Cal Central, Kelly says.
Oh, okay.
So that's, yeah, for changing from pass fail to letter grade. But our grades for the exams and the course, I guess we can put up on B courses. Is that right, Maria?
Yeah, we'll still keep putting everything on B courses.
Yeah, okay, great. Okay, other questions? All right, yeah, so I mean, I really want to emphasize again, I hope you can focus on learning as opposed to worrying about your grade. You should note that this same sort of situation is true at essentially every other university in the country, at least. And so everybody will have a strange semester or term where they might have all pass-fail grades, for example. So this, I don't think this will have any impact on getting into graduate programs or medical schools. Okay, so let's go back to thinking about electron transfer chemistry. And so last lecture, we went through the details of inner sphere electron transfer reactions. And these, of course, are electron transfer reactions where you form a covalent bridge between the two metals, and the electron transfers through that bridge. Today, we're going to go through the details of outer sphere electron transfer reactions. And so these are electron transfer reactions where we don't form a covalent bridge, but the electron transfer reaction still happens. And so here you see a table with a list of some example reactions. And so if we start, let's start at the bottom. So for cobalt-2 hexaammonia, the self-reaction with the cobalt-3 hexaammonia complex, these are both oxyhedral complexes, and you can measure the rate of electron transfer between the two. And you can see it's actually very slow. So 10 to the minus 6 for that rate constant. And we can compare then with a couple of other cobalt-2,3 self-exchange reactions. This one with ethylene diamine is slightly faster. And then this one, but still quite slow at 10 to the minus 4. And then we have one with phenanthrene, 3 chelating phenanthrene ligands, which is much faster. So if you think about this, one of the important keys to understanding why these reactions at the bottom are slow is to recognize that there's a change in the spin state. And that change in the spin state, where you're converting when you do an electron transfer from a high spin configuration for the cobalt-2 complex to a low spin electron configuration for the cobalt-3 complex, this leads to a large change in the bond lengths. And generally, it's observed that large changes in the metal ligand bond lengths for one of these self-exchange reactions results in a very slow outer sphere electron transfer reaction. Okay. So if we think about cobalt phenanthrene 2+3+ self-exchange reaction, here you have some electron delocalization of the d electrons on the cobalt onto the phenanthrene aromatic system. And what this means is that there's much more similar bond lengths for the cobalt nitrogen bonds in the 2+ and 3+ complex here compared to the ethylene diamine or ammonia ligated species. And so a second observation here is that reactions for complexes where you have significant delocalization of the d electrons onto the ligands are faster. If we then look at the iron complexes, then you can see we've got two here. And the situation is somewhat similar. For the iron hexaquo complex, the 2+, 3+ self-exchange reaction, you do have a significant change in bond length because the iron 3+ ion is smaller radius. And in this case, you then see a reaction that's not as slow as cobalt hexaammonia. It's intermediate in its values that we're seeing here. And so this has to do with the fact that you don't have a spin state change from high spin to low spin. Here, the iron is going to be high spin in both cases, but you do have some bond length change. For the bipyridine self-exchange for iron 2 and 3, at the top, you can see this is a very fast reaction. So 12 orders of magnitude faster than the cobalt hexaammonia reaction. And this is a case where, again, you have delocalization. These are actually low spin complexes. And you have delocalization of the electron onto the bipyridine ligand. And you'll also note that when we do this reaction involving low spin iron 2 and iron 3, you don't have any electrons in the Eg star orbitals, right? And so there's no anti-bonding type contribution that might lead to greater bond distance changes. And so the bond distances between the iron 2 and iron 3 bipyridine complexes are very similar, and this leads then to a fast exchange rate. And similarly, when you go down the periodic table to osmium for that same type of complex, again, the reaction is extremely fast. The bond distances metal to nitrogen don't change much. Okay, so these are observations that we're going to try to explain today. So we're going to think in detail about the steps involved in these kinds of, particularly these self-exchange reactions. But we can note that there are, of course, also the possibility of doing, instead of a self-exchange reaction, you can have a spontaneous electron transfer reaction where it's downhill to transfer an electron from, say, osmium 2+ here to molybdenum 5 in this octocyanide complex, right? And so those reactions that have this delta G driving force, in these cases, they're all quite fast. Right. Okay, so let's think about the mechanism in detail. So if we think about this self-exchange reaction for iron hexaquo complex, 2+ and 3+, let's suppose we're doing a reaction where the iron 3 is isotopically labeled and the iron 2 is not. Then we can monitor this self-exchange rate constant. And the thing to note is this figure attempts to show that the iron 2 complex has longer iron oxygen distances. It's a larger species compared to the iron 3. And so if in this reaction, we expect these two molecules will diffuse together. And when they're close together, they're then going to form the loosely bound precursor complex, and electron transfer will happen. And so this is involving a large change in geometry, and it's comparatively slow. If we compare with iron hexacyanide 4-, 3-, that self-exchange reaction is significantly faster. And so the difference here is that the bond distance, iron to carbon, in these two species is very similar and very little difference. And so we don't have the same large motion necessary when we do an electron transfer reaction. And this has to do now, understanding why this is going to have to do with recognizing the fact that electrons move quickly compared to nuclei. So let's imagine one of these reactions happening. So Audrey has a question. Actually, people are welcome to, it's hard for me to manipulate the chat, so you're welcome to raise your hand and ask verbally. But Audrey's question is, how come in the products the iron 3+ still has longer bonds? So there's no, so the point here is that I'm going to answer that. I was just about to answer that. That's a good observation. So the point is that when we do the electron transfer, the electron will transfer very rapidly before the nuclei have a chance to respond. And so when the electron transfer happens, we're going to create an iron 3+ cation where the waters are still far from the iron center. And for the iron 3+, which has waters close, when the electron transfers, the nuclei will still have the waters close to the metal. And so what it looks like is we're going to do this electron transfer, and we're going to create excited states of the products, right? This would be an excited state conformation of the iron 3. It would then have to relax to the ground state and emit energy. This also would be an excited state. The iron 2 wants to have longer bond distances. It would then relax to the ground state and release energy. Right. So this is this is in accord, of course, with the Franck-Condon principle that electron transfer will take place much faster than the nuclei can respond. So that's why this iron 3 is initially going to be in this excited state geometry, and the iron 2 as well. And so this brings up a contradiction to the first law of thermodynamics, right? Because here we're going to do a reaction, and it's overall, there's no free energy difference between reactants and products. We're just exchanging an electron. But according to the Franck-Condon principle, we're going to have to do that in a way that's going to put the molecules into excited states, right? And it should be noted that these self-exchange reactions proceed in the dark. You don't need some light to promote the iron complexes into some excited state. And so this looks to be a violation of the conservation of energy. And so that was very widely debated for many years. Why, how do you resolve this? And a chemist named Rudy Marcus, proposed a theory that resolved this situation. So here's a picture of Rudy. This is our hero for today. And Rudy Marcus is, you can see here, he was born in 1923, so almost 100 years ago now. But he's an amazing scientist. He still has an active research group at Caltech. He still goes and gives seminars. He visited Berkeley, I think, last year and gave a seminar last spring. So he's had an amazing career, but his claim to fame is developing a theory for this type of outer sphere electron transfer reaction. So Marcus he's originally Canadian. He grew up in Canada. He went to school and did his PhD at McGill University in Montreal. He then moved to the US, became a US citizen. He did a lot of his seminal research at the Polytechnic Institute of Brooklyn. So a lot of the theory that he came up with was there, and then subsequently at University of North Carolina. And after that, he moved to University of Illinois, and then finally to Caltech. But for his contributions to understanding electron transfer reactions and resolving this discrepancy where we appear to be violating the first law of thermodynamics, he won the Nobel Prize in Chemistry in 1992. All right, so there is a nice paper that we've uploaded to the B-Courses site. It's this Angevanta Chemie paper from 1993. And Angevanta Chemie does a nice review article for each chemistry Nobel Prize that's awarded. And so if you're ever interested in sort of understanding the science behind a chemistry Nobel Prize, this is a great place to look. And so here, this article, which I encourage you to read, Marcus, it's based on his Nobel lecture, but it gives a historical perspective of how he developed this electron transfer theory. So we're going to go through the steps of this reaction and theory. And this will be the elementary steps for particularly an outer sphere reaction. But you should keep in mind that the theory also applies to inner sphere electron transfer reactions once you've formed the bridged intermediate species. That part is the same for an inner sphere reaction. Okay, so we're going to have 5 elementary steps for an outer sphere reaction. And in the first step, the reactants will diffuse together to form a precursor complex. And that might require some work. So for example, if you're trying to bring an iron 2+ complex together with an iron 3+ complex, those charges are repelling each other and they don't want to get together. So the reactants coming into proximity that will allow an electron to hop from one metal to another is the first step. The second step will be thermal activation. And so this is the key. This is how Marcus got around this apparent violation of the conservation of energy. He said that what's going to happen here is thermal energy is going to activate the metal complexes in this precursor species. And when it's activated at a point where the atomic positions correspond to the transition state, where all the nuclei are in the right positions for the transition state, when you happen to hit that configuration, thermally, then all of a sudden the electron can transfer and the reaction will proceed. Right. So the third step would be at that transition state geometry, the electron transfer suddenly occurs. And after that, then you've got, you can relax to the ground state of the products. So they're still next to each other in this successor complex. You haven't moved any nuclei during the electron transfer. In step 4, now the nuclei will respond to the electron moving from one metal center to the other and relax into their ground state geometry. And then finally, the products will diffuse apart, and that can have some work associated with it. Okay, so we want to consider this mechanism in more detail and look at how Marcus came up for a way of modeling these reactions. So just graphically, this is a diagram that takes you through each of the 5 steps. So let's go through this just to make sure everybody's clear what's happening. So the first step is we're going to start with a donor complex. So this is the species that's going to give up an electron, and an acceptor complex. This is the species that will accept the electron. And initially they're in solution, they're free to diffuse about, they're not necessarily close to each other, but we're going to do some work, bring them together, and form this precursor complex where they're close enough that an electron could hop from one metal to the other. And so then once they're in this precursor situation where they're near each other, we're going to need them both to be thermally activated into the transition state geometry. And so they're going to change in size. Generally, the species with the extra electron is slightly larger. The donor is slightly larger than the acceptor. And so changes to the geometry of the complex are shown here to make them equal for a self-exchange reaction. So these circles containing D and A represent the metal and its ligands. And these outer smaller circles, these represent the first solvent shell surrounding the precursor complex or the metal complexes, right? And so you have solvents often with a dipole. And so in creating the activated complex, you need to not just thermally activate the donor and acceptor towards the transition state, but you need to also get all of the solvent, surrounding solvent cage into the activated complex geometry. And once you achieve that activated complex geometry, then all of a sudden the nuclei are all in position and the electron transfer can occur. And so this is the electron transfer step, the third step. The electron's going to move from D to A. And I want to note that there's a mistake in this figure. The surrounding solvent nuclear positions should be identical top to bottom here. For the activated complex, all of the nuclear positions are identical. The only thing that's happening is an electron is moving from D to A, from metal to metal. Okay, so, and then after that happens, the nuclei can respond, and you can form then the ground state geometry for each of the metal complexes, and the nuclei of the surrounding solvent can also respond to better solvate after that charge transfer. And then finally, okay, Amy, please go ahead and ask your question.
question is to the arrow directions. So in the activated complex, the arrows are pointing like towards the well, away from the donor and towards the acceptor. And so is that a charge relationship, like a dipole? And if so, why do they start going in more random directions as it relaxes and it's solvated?
Yeah. So those arrows are indicating either a dipole or an electron polarization of the solvent, or both. And you know, generally, I wouldn't take this to mean too much, but we're going to talk later about there is a difference between nuclear motion and electron motion for the solvent molecules. So these arrows, if you take them to mean the dipole, reorienting the dipole would require moving the nuclei of the solvent. And so the key thing is that's not going to happen. That part is not going to happen during this electron transfer step. In terms of the ground state configuration, the dipole orientations will depend on the specifics of how the charge is arranged in the metal complex. So I don't think you want to take this too literally in terms of where the dipoles are pointing. Just recognize that after the charge transfers, there's usually going to be a change in how those dipoles are oriented, and those will involve nuclear motions. Good question. Okay, so once you've got the successor complex, then those two species, those two metal complexes can diffuse away, and there could be some work involved in bringing them apart. Okay, so then we've gone from reactants to products. Any other questions so far on this mechanism? Please speak up if there are.
I was wondering with the activation step, whether that's just something that happens regardless of whether the electron transfer reaction takes place?
Yeah, that's actually, we're going to talk about that next. So the probability of electron transferring once you reach that activated complex geometry has to do with if it's an adiabatic reaction system or not. And so I think that's your question. So we're going to discuss that now. That's part of Marcus's theory. His theory is specific to adiabatic reactions, where when you reach that activated complex, you go on to do the electron transfer reaction. We'll get to that in just a second, but before we do, I want to point out this is a rather typical energy profile for the free energy of one of these reactions. So this is just the reaction coordinate versus delta G. So we're going to start off with the donor and acceptor in solution. Here we're going to bring them together. There may be a barrier forming the precursor complex. We'll form the transition state geometry. Electron transfer will occur. We'll relax to the successor complex, and then those can diffuse apart. And so this is very similar to the profile for one of the types of inner sphere mechanisms we considered, where this getting into this transition state for the electron transfer reaction is generally the rate determining step. All right. So Marcus said, we'll come to adiabaticity in a minute, but Marcus said he came up with his theory as to the reaction, the reactants and products, their potential energy wells, and how they would get over the activation barrier to do the electron transfer. So modeling that central electron transfer step, we can have a well associated with a precursor complex and a well associated with a successor complex. And the activation energy in that reaction coordinate diagram is shown here. But Marcus's theory is going to relate these two parabolas. And so in one of these reactions, we're going to have, if it's not a self-exchange reaction, there'll be some driving force. There'll be some delta G associated with the reaction. And the understanding Marcus's theory is all about understanding where these parabola intersect and what delta G will be. Delta G of activation. So we're going to look at this in more detail. But here's Marcus's theory, simple theory that he derived using transition state theory. And it's a very nice way of predicting these rate constants. But Marcus said that this rate constant for an electron transfer reaction should be kappa times Z times an exponential of minus this activated complex energy divided by RT. So here Z is what's called the frequency factor. This is going to be something about how frequently a reaction attempt might be made. And this is on the order of 10 to the minus 11 attempts per second at room temperature. And then kappa is going to be what's called the adiabaticity constant. So this has to do now with the probability that electron transfer will occur when you reach that transition state geometry. And so we say if it's an adiabatic system, then that probability is 100%. If it's non-adiabatic, then it'll be some smaller percentage of the electron transferring and the reaction going to products. So part of Marcus's theory was to recognize that the degree of adiabaticity here is correlated to or proportional to a exchange electronic coupling energy, which we call HDA. And this is very similar to an exchange energy when we think about orbital wave functions, right? And the stronger the exchange between the two systems, reactants and products, the greater this will be, and the more likely the reaction will proceed, and the closer to 1 kappa will be. So this exchange, this electronic coupling energy between the reactants and products is going to depend on the overlap in energy difference between the donor and acceptor orbitals in the transition state. So what this means is that electron transfer step, whether or not it proceeds, has a lot to do with if there's a reasonable orbital overlap and energy match, that just like we considered in MO theory, that enables, facilitates the electron transfer. So as you can imagine, for a lot of the inner sphere reactions that we considered, then there's going to be a very obvious, perhaps, pathway for electron transfer, and those we might think would have a stronger coupling energy. So Marcus theory in principle only really applies to kappa near 1, so adiabatic systems. So let's graphically look at a representation of that coupling energy, that electronic coupling energy. So this is the degree of coupling where those two parabola would cross. So remember, we had a parabola for the donor acceptor precursor complex. We had a parabola for the donor acceptor successor complex after electron had transferred. And the coupling between those electronic states is going to open up a gap. And the bigger that gap, the more likely this reaction goes forward, right? So that should be fairly clear. So if you have a strong coupling in that activated geometry that enables the electron transfer, you'll open up a big gap. That'll be what we can call a strongly adiabatic kappa equals 1 system. If the gap is smaller, relatively small compared to that large gap, then it'll be, we can call that adiabatic. Kappa is close to 1. If it's HDA is really small, but still there, but still finite, then what'll happen is often when you reach that crossing point, you won't transition to this other product state. You won't transfer the electron, you'll just reach the transition state and either continue vibrating to some other state or relax back down, but you'll stay in the well of the reactants. But very occasionally, some small fraction of the time, you might form products. So this would be a non-adiabatic system. And then finally, strongly non-adiabatic you could take to mean there's really no chance of electron transfer occurring when you reach that geometry. There's just no way, no pathway for the electron to move. Okay, any questions on this? If so, please speak up. All right.
When we're
Yeah, go
talking
ahead.
about adiabatic systems, which complex are we referring to?
So we're referring to, so the left-hand well is for the precursor complex, and the right-hand well is for the successor complex. And the coupling will be to have to do with how facile the electron can move in that transition state geometry. Does that answer your question?
I guess I'm a bit unclear on how the precursor complex needs to absorb thermal energy in order to become activated, but then once it's activated, it's no longer, it's adiabatic.
I'm not sure I followed that. So which panel are you looking at in this, or thinking about when you're saying that?
So if you could go back 2 slides, I think, to the one with the circles. One more slide. Oh, yeah, this one. So from what I understand, we need from the precursor complex that needs to absorb thermal energy in order to become activated. So that's non-adiabatic, correct?
Right.
But then once it's in the activated complex, it then becomes adiabatic somehow?
Yeah. So the adiabaticity and that kappa factor is just for this electron transfer step.
Okay, got it. Thank you.
Yeah. So, and it really has to do about, you know, the particulars of how the electron transfer could occur through comparing the two wave functions for the precursor complex, this one here, and the successor complex. Connor, go ahead.
Can you clarify for me what, especially in the strongly adiabatic and adiabatic case, what that upper curve or which the two different curves are, please?
So here you take the two parabola, but once you reach that, this is a non-crossing point. And so if you imagine, remember when we were thinking about deriving electronic energy states for transition metal complexes, we came up with the non-crossing rule. And that basically had to do with, the fact that you're going to have, when you get close in energy, if you have good overlap, then you're going to have coupling that leads to opening up this gap, and there's no crossing of the energy states. So that's what's happening here between the parabola for the precursor complex and the parabola for the successor complex. This is not a great drawing. The parabolas do not look very parabolic here, maybe. Does that answer your question, Connor?
Yep, thanks.
Yeah. So just think about it, a non-crossing gap opens up at where those cross. Okay. And yeah, as we'll see, again, Marcus theory is really all about interacting parabolas and how they cross, where they cross. Okay, so Marcus went further and came up with an expression for this transition state free energy. And so here's the expression. It's going to have a term associated with electrostatics, and then a term associated with what we'll call the reorganization energy. So this first part here, this part is an electrostatic energy contribution. And so this is, if you're bringing together, for example, a 2+ and a 3+ complex, then there's going to be some repulsion between those species in forming this activated complex. So that's going to contribute to the free energy. And so that involves the charges on the donor and acceptor. This is charge of the electron. This is radius of that precursor complex, which is taken to be the sum of the radii of the donor species and the acceptor species. And so this is then going to be modulated by an ionic strength factor. So how, if you have a lot of salt in your solution, you can screen that charge. And the dielectric constant, it's inversely proportional to the dielectric constant of the solvent. So if you have a high dielectric constant, then that solvent will be very good at screening the charge of the donor and acceptor, the charges, and reducing this electrostatic energy contribution to the free energy. So for example, water has a dielectric constant of 78. And so with 78 in this denominator, this term gets relatively small. Methanol has a dielectric constant of 33. And so that's going to be have less screening of charges, and therefore this will be more of a contribution. Toluene, if you're using a solvent like toluene, it's got a very low dielectric constant, and it's about 2, and so it's very poor at screening charges. and therefore this term will become more important. All right. So then in the second term here, we've got lambda, which we're going to get into in detail, which is the reorganization energy. And this will have to do with two parts. It's going to have an inner sphere part and an outer sphere part, lambda I and lambda O. And the inner sphere reorganization energy is going to be the energy required to move the ligands bound to the metal into the transition state geometry. And then the outer sphere part is going to have to do with moving the solvent molecules in the surrounding cage into the transition state geometry. And so it's lambda over 4 times 1 plus the delta G for the reaction, plus the work involved in bringing the species together and pulling them apart. So it's that quantity over lambda, overall quantity squared. Right. Okay, so let's think about a couple of things here. First of all, for solvents with a large dielectric constant, we're going to have a situation where this factor is essentially negligible, and they're going to screen the work involved in bringing the any charged species together. And so then this will reduce to delta G, and so we'll simply have this expression here. So for large dielectric constants like water, this simplifies, and a lot of the reactions we've considered, essentially all of them so far, have been in water. So this very simple formula where you just need to know the free energy of the reaction and then some estimate of the reorganization energy, and you can predict the delta G, and therefore from the previous equation, the rate constant. Okay. Oops. And so, yes, from that we can then extract an expression for the rate constant. According to Marcus, it should be as shown here. This is just substituting what we derived for delta G double dagger. Any questions on this equation so far? We're going to go into lambda in detail next. Okay, so we can then use that equation and plot what we would expect. And so this is a case where we have a reaction where lambda is equal to 20 kilocalories per mole. This is just plotting the free energy versus the driving force, the free energy of the reaction. So vertical axis is free energy for the transition state, forming the transition state, and then this is free energy for the overall reaction. And so what you see here is quite interesting. So if you start to increase the, let's see, so here if you've got a downhill reaction, if you start to increase the driving force for the overall reaction, you can see the delta G of the activation energy should be decreasing, the reaction's getting faster and faster and faster. Oops, sorry. But what this theory predicts is that as you lower this as you increase or give a stronger and stronger driving force, more and more negative delta G for the reaction, at some point where you've matched the reorganization energy for forming a transition state, once you go past that, the reaction will no longer speed up. So you're increasing the driving force for the reaction as we move from right to left, but past minus 20 kilocalories per mole, all of a sudden you've got a greater driving force, but the reaction's slowing down. Delta G of activation, the activation energy is getting larger again, right? And so this is this region that's labeled the normal region, where delta G is above minus 20 kcals per mole, larger than the reorganization energy. This is what we would normally expect. When we increase the driving force, the reactions go faster. This region out past minus 20 kcals per mole, this is what Marcus called the inverted region. And this was a prediction made by his theory that was very strongly debated for many years. And so there was a lot of debate if there is really an inverted region. Nobody had ever observed it rigorously. And that was a big question for his theory. And so that debate went on for almost 30 years before finally there was experimental confirmation that the inverted region definitely can exist. And since then, there have been many confirmations. But that was really a great triumph for Marcus's theory and a lot to do with him getting the Nobel Prize. All right, so here Marcus has predicted that for large dielectric solvents, we're going to have these two intersecting parabolas. And as we move one parabola, the product's parabola lower and lower relative to the reactant's parabola, will eventually reach a value where delta G is 0. There's a barrierless reaction, and the speed of the reaction is maximal. And it's going to be, he predicted it would be equal to the negative of the reorganization energy. And if you continue to increase or decrease, but increase the magnitude of delta G, the driving force, then delta G double dagger would start to increase, leading to this inverted region, in which electron transfer reaction slows down as the driving force increases. Right. So this is very, initially at least, very counterintuitive that this should be possible. So let's consider further what's happening here via these potential surfaces. And this is a plot that has some good parts and some bad parts to it. But it shows what's happening as we move these parabola around. And the parabola are labeled incorrectly in this diagram. This should actually be, the left parabola is the precursor complex, the right parabola is the successor complex. These should be labeled reactants and products, or precursor complex, successor complex. And so if you have, you could have this situation where there's no barrier to the reaction. You could have a situation where there's some small barrier. And in the reaction coordinate here, as you thermally activate, you can see, the reactants are looking more like this transition state, and we're actually rearranging the species to look more like the products. Right? We're moving along the reaction diagram from left to right. Right. And then in C, if you continue to raise this parabola, you get to a point where you can actually, because these are parabolas, the activation energy for a self-exchange reaction or an isoergonic electron transfer reaction will be the reorganization energy divided by 4, right? Just simply by how two parabolas intersect. If you continue raising, you can have an endergonic reaction, an uphill reaction with a small barrier. If you drop delta G or make the reactants and products look more similar, then you can get to this state where you can form a transition state here and then convert to products. But when you're doing this, the counterintuitive thing is that in this inverted region where you have a large driving force, you're actually activating the precursor complex to look less like the products. So we're going the opposite direction in the reaction profile. And then you reach that transition state, and then you can relax all the way down here. Okay, so whether or not this existed was a good question. So the problems with this diagram, they're really twofold. First of all, these are not good parabola drawings. Second of all, the labeling that I already pointed out. Here's a maybe a better drawing for how the parabolas look. So here you can see this is for a self-exchange reaction. There's the activation energy. Here's the normal region. Here's the point where we get to barrierless reaction. And as we continue to lower the product parabola and increase the driving force, then we get to this inverted region where, where as we're modifying and making the driving force larger and larger, the reaction is actually slowing down. Okay, so any questions? If so, please speak up. All right, if not, let's look at this is the paper that was the first experimental demonstration that the inverted region existed. So this is an experiment where they made molecules that look like this. So you've got a biphenyl unit on one end, and you've got a sort of steroid saturated hydrocarbon intervening part that's very rigid. It holds the donor and acceptor apart. And then there's going to be some acceptor component covalently attached here, A. So A is going to vary across the series of species shown here through this, and it's appended through this bond here. And so what's happening in this data and in this paper, this is a really classic paper for electron transfer reactions. So it's from 1984. It's only a 2-page paper. We've uploaded it to the course website, and you can take a look. But what they do here is they use an electron beam at a high energy beam of electrons at Argonne. So Argonne has had a facility called LINAC, and they can pulse a solution of these molecules and create essentially essentially free electrons into the solution. And those free electrons will non-discriminately reduce species, and so they will, with equal probability, put an electron here. And then from the absorption spectrum, they could watch the rate for an electron injected here to transfer to the acceptor. So when the electron pulse puts an electron near a biphenyl, that electron wants to transfer to this acceptor species, either these or these anthraquinone or these quinone type, naphthoquinone type species or quinone type species, or these extended aromatics. Those are going to be the acceptor parts of the molecule. So this is actually an inner sphere reaction. And the points that you see are varying the acceptor and thereby varying the driving force. Right? And so as we get to stronger driving force, the rate constant, initially it's increasing as we normally would see. But then out here, now you're increasing the driving force significantly, and but the reaction starts to slow down. Right? And so the solid curve you see was calculated using Marcus's theory and some specific parameters to try and match the data. All right, well, so that was a really key experiment. And after this, later, it was shown by Harry Gray and others that this inverted region could also exist for outer sphere transition metal complex reactions. And so let's consider now this all-important reorganization energy. So remember, this has two parts. It's the inner sphere reorganization energy plus the outer sphere reorganization energy. So first of all, the inner sphere part. So what's happening here is we're going to need to move the nuclei into the position of the transition state for the metal complex. So the ligands will move, and we can actually use vibrational modes of the transition metal complex. That's what thermal activation will do. It's going to activate vibrational modes, and those vibrational modes have to take us, some combination of those have to take us to the transition state geometry for the inner sphere. And so associated with that, we have some specific modes and involving the metal ligand distances and the reactants and products and how much those change, and a reduced force constant associated stemming from the reactant and product force constants. So all of these could be estimated based on our understanding of the vibrational modes of the individual complexes. And for octahedral complexes, this is only going to require the symmetric breathing mode. And so let's consider now a self-exchange reaction. So in a self-exchange reaction, delta G is 0, and you can directly then measure the inner sphere, or rather the total reorganization energy. And the most important considerations in that case will be changes in the bond strength. So if electron transfer changes the population of the EG star orbitals, then that will have lead to a significant difference in bond lengths. And of course, that will take stronger vibration activation, more thermal energy to activate to move those nuclei. And then the second important consideration will be differences that in the size and the bond lengths according to the charge of the metal changing the radius of the metal ion, and therefore the size of the donor versus acceptor complex. All right, so this really has to do with the difference in bond lengths and ligand arrangements around the two different charge states for the metal. And if it's a large difference, then we should expect a large activation energy. If it's a small difference in metal ligand bonds, then it should be a fast reaction and a small delta G double dagger. Okay, so just to give an example, we can compare these reactions for cobalt-2 and cobalt-3 plus complexes for ammonia, ethylene diamine, and this new ligand, which we'll look at in a minute, called sepulcrate. And so here are the bond length differences. So because we have a change in spin state, there's a very large difference in the 2+ and 3+ bond lengths. Cobalt to nitrogen, it's about 0.2 angstroms. And that's true for all of these reactions. And because that's a large delta change in bond length, this reaction is very slow for the top two complexes. But the sepulcrate complex shows you a way that you can potentially speed up such a reaction. So let's take a look at that. So here's the crystal structure of the cobalt-3 sepulcrate complex. And so here's a line drawing of what this is a cage ligand where you've got 8 amine sites, 6 of which can coordinate in a octahedral type geometry. So this is a very rigid cage, and it's not very flexible. And once you get the metal ion into this ligand, it's like in a sepulcher. It's really confined there, and it's not coming out. So hence the name sepulcrate. But what's happening here, the reason this reaction is faster is that the strain, there's considerable strain in this hexadentate sepulcrate ligand. And that strain is placing the molecule into what's called an entactic state. And so an entactic state is a case where the rigid ligand strain positions the complex closer in energy to the transition state energy. Right. So what that means is that actually, when we form the transition state, some of the strain of the ligand is relaxed relative to the strain in the cobalt-2 or cobalt-3 complex. Right. So that's summarized here. Here, ligand strain is relieved in the transition state relative to the reactant and product complex geometries. So that's an important effect where you're moving and essentially lowering the activation barrier by releasing some strain in the surrounding set of ligands when you form the transition state. So you want to achieve that sort of entactic state, you want to try and use a ligand where its strain will relax when the transition state is achieved. And the transition state here we would expect would be somewhere in between this delta change in bond length of 0.2, maybe where they're both around in between at a 0.1 difference from their starting distance. Okay, so finally, in the last couple minutes, let's consider the outer sphere reorganization energy. And so there are two important contributing factors here. First of all, there's going to be a change in the geometry of the inner sphere, right? And so that is going to require a response from the solvent. So the solvent, after you transfer the electron and those geometries change after relaxation, the solvent positioning will be different. And so in the activated, or the transition state geometry, the solvents will arrange in some into that activated complex geometry, but it'll be different from the starting reactant precursor complex arrangement, or it'll be, sorry, the reactant arrangements and the product arrangements. And then secondly, there'll be a redistribution of charge. So if there's a large change in geometry, large inner sphere reorganization, we might expect lambda O to be relatively large. And if there's a large redistribution of charge, then the dipoles might actually need to change. And so that requires solvent rearrangement, and that can lead to a large lambda O. And so you can actually estimate these, this reorganization, this part of the reorganization energy, by treating the solvent as a dielectric continuum and modeling the donor and acceptor metal complexes as spheres. And so the larger the sphere, of course, the less the charge of the complex will be impacting the solvent arrangement. And so the smaller the lambda O. The greater the change in charge for the reaction, the larger the response of the solvents should need to be. And then there's a part here that has to do with the dielectric constants. And so there are two dielectric constants here. One is the optical dielectric constant, and that's just related to the refractive index of the solvent squared. And the second is the static dielectric constant. These are things you can look up. But the point is the optical dielectric constant, that's the response of electrons moving. And remember, electrons can move fast compared to nuclei. So when the electron transfers from metal to metal, you can also have electronic changes in the surrounding solvent cage. And that would be part of this term. So the solvent can respond electronically depending on the polarizability, usually, of the solvent. And then the static dielectric constant, this is going to have to do with nuclear rearrangement. Okay, and then so we're out of time, but the main point here is this outer sphere reorganization energy will increase with increasing delta E, change in charge, and increasing solvent polarity. More polar solvents are going to have to rearrange more. Decreases, it's going to decrease with increasing radius. The solvent molecules are further from the charge, and solvent polarizability. So solvent polarize, if it's a very polarizable solvent, the electrons can move around easily and try to respond to the metal-to-metal electron transfer. Okay, so we're out of time. I want to just mention, finally, there's going to be, the next couple of lectures, you're going to have some guest lectures. And so these are experts. First will be Dr. Megan Jackson, who's an expert in electrocatalysis. She did her PhD in electrocatalysis, and she's going to give you a taste of that and perhaps some of her research. And then on Tuesday, Dr. Brandon Barnett will be lecturing, and he's an expert on transition metal reactivity and catalysis. And so he'll give you his perspective on that. All right, good. So have a good rest of your day, and we'll see you on Thursday.